In this lesson, we're going to learn about chemical kinetics, or how fast reactions occur. So for example, we have fireworks, which happen very quickly, or the formation of stalagmites and stalactites, which take many, many years to happen. So the word or term reaction rate, or rate of reaction, is just referring to the speed that a chemical reaction occurs at, so how fast a chemical reaction is happening. Or we may talk about the change in the amount of reactants that are being consumed or used up, or the change in the amount of products that are being formed over a particular time interval. So our rate is equal to a change in quantity, so that can be of reactants or of products, divided by a change in time. So we can measure a rate of a reaction in multiple different ways, usually depending on what type of reactants and products you have. So if we have a gas being formed, then we could measure the volume of that product being formed using a gas syringe. So in that case, our rate would be a change in volume over a change in time. So that change in quantity, there's different ways that we can measure that quantity. We can measure a change in mass, so whether that is mass of reactant reducing as it's being used up, or the mass of product being created. So we'd use a balance for that, and in that case our rate is our change of mass over our change in time. If we have a temperature change happening, whether it is an increase if it's exothermic or a decrease if it's endothermic, we can use a thermometer for that, and that would be the change in temperature over the change in time. Once again, if we have a gas, we can measure the change in pressure. So we could use volume, or we could use a pressure sensor and measure the change in pressure. We can use a spectrophotometer, which will measure the change in the light based on the particular wavelength of the color of reactants or products. So that would be a change in absorbance of the light that is being measured there. If we have changing between acids and bases, we can measure the pH. So in the next unit, we will talk about pH and how that is a measurement of how many hydrogen or hydronium ions there are. So we can measure a change in that, whether there's an increase or decrease. And we'll also learn about pOH, which has to do with how many hydroxide ions there are. So we can use a pH meter for that and measure the change in pH over the change in time. And another way would be electrical conductivity. So the change in concentration of dissolved ions will change the conductivity. So whether that might be an increase or a decrease. So we can use an electrical conductivity probe there to measure the change in conductivity over change in time for rate. So many different ways that we can actually measure how quickly reactants are being used up, or products are being formed. So we will often talk, though, about reactions, reactant and product amounts in terms of concentration. So here's a visual that just shows reaction occurring. So at the beginning we have reactant molecules, which are reactant A here. And as those collide, they form the product B. So here we can see we have fewer reactant A molecules and some product B molecules. And as time progresses, we have more and more product being formed and less reactant that is available. So if we had information on our time and the concentration, so these square brackets around a substance means concentration of that. So this would mean concentration of A, and this here is being measured in millimoles per liter. So there I would take my final concentration, subtract my initial concentration, and then also my final time, subtract my initial time. So that's the change in concentration over the change in time. And that will give me the reaction rate. So that is for reactant A being used up. I could also find, if I had information about the concentration of product B, I could also use that change to measure the reaction rate. So within a particular reaction, we can actually graph both the consumption of the reactants and the production of the products. And what you can see here is that these reaction rates are equal but opposite. So the same rate that reactant A is being consumed is the same rate that product B is being created. So our reaction rate, our change in the concentration of B over the change in time, is equal to the reverse of the change in concentration of A over the change in time. So we have B would be the reaction, there would be positive because it is being created. Now we always write a reaction rate as a positive amount, and so if we're using our reactants, this would be negative because we have a decrease happening here. And so we have a negative in front of there to make our reaction rate value a positive value. So we always talk about reaction rates in a positive amount. So we can measure reaction rates in different ways. We can talk about a change over a given time period. So it can be over the whole reaction. We can calculate our average reaction rate from there using the very initial and the very final points there. And that would actually give us a slope that is like this. So there are parts during the reaction where our reaction rate is actually faster than that average over the whole time, and there are times that it is slower. So we can see at the beginning when there are a lot of reactant molecules, we have a quick reaction rate, and then it starts to slow down as we are using up our reactants and there aren't as many there. So the average rate of reaction is just the change in reactant or product concentration between 2 points. So that can be between these 2 points, we can look at an average rate, or we can look for the whole process. So at any point, we can pick 2 points and calculate the average between there. We can also calculate the instantaneous rate, which we can pick any point along the graph that we want, and then we just draw in a tangent line. So a tangent line is just a straight line that is drawn in at whatever point we are looking for the instantaneous rate at. And as we move out from the curve, we should see an equal distance between the curve and our tangent line on both sides. And then once we have our tangent line drawn in, we can calculate the slope of that, and that will give us the rate at one particular instant. So an instantaneous rate of reaction is looking at how fast a reaction is occurring at one particular point. So if we take a look at this example, I believe this is hydrazine. So 3 hydrazine will react to form 4 ammonia and 1 nitrogen. So as we talk about our reaction rates, what we need to take into account the stoichiometry. So for every 3 hydrazine that gets used up, 4 ammonia are being produced. And so my rate of consumption of hydrazine is 3 moles for every 1 mole of nitrogen that is produced. So I have a 3-to-1 ratio there in terms of my reaction rate for this particular equation. And so my change in concentration of nitrogen is going to be equal to -1/3 of my change in concentration of hydrazine. So if I calculate my change in concentration of hydrazine, as I look at this, for every 3 hydrazine that gets used up, only 1 nitrogen is produced. And so if I'm looking for, at that same time, the rate of reaction of nitrogen production, it is 1/3 of the rate of hydrazine consumption. So the negative accounts for the fact that hydrazine is being used up, so over time there's less of it, over time, nitrogen is being produced, so there's more of it. So the negative will account for that change, and for every 3 hydrazine, there are only 1 nitrogen. So the 1/3 there will account for that. So the change in production, the rate of production of nitrogen is equal to negative 1/3 of the change in consumption of hydrazine. So if we're going to talk about ammonia relative to hydrazine for this same equation, so our change in ammonia, here we go from 3 to 4. So to get to there, if I divide 3 by 3, I get to 1, and then I would need to multiply by 4 to get to 4 ammonia. So that means 4/3. So multiplying by 4, dividing by 3 is my rate of production of ammonia in comparison to my rate of, rate of production of ammonia in comparison to the rate of consumption of hydrazine. So there's my change in hydrazine concentration. So the negative is going to account for the difference in consumption versus production. And then I have divided by 3 and times 4, or as we write it as a fraction, 4/3. So multiplying by 4, dividing by 3. So that is how we can calculate the change in rate of any particular reactant or product based on already knowing the rate of another. So our stoichiometry comes into play here.